Okay.
Let's hear the opening address by the president of APCTP, Professor Yunkyu Bang. Okay, Yunkyu, please.
Okay, good morning, everybody, and thank you very much. Of course, today's lecturer, Professor Misao Sasaki, and all the participants. And this is a special lecture arranged by APCTP. And I am very pleased to have Professor Misao Sasaki today. And this special lecture is arranged not only because Misao Sasaki is world-leading scholar in cosmology, but also he was very recently appointed as APCTP Distinguished Professor to serve the senior advisory group in order to give mentoring to our in-house researchers and some possible collaboration with the researchers in APCTP. But as you know, because of this terrible corona pandemic, he cannot visit us in short time, so that we have arranged this special lecture. So although he's sitting currently in Kyoto at his home, he can appear in Pohang and everywhere, thanks to the modern technology. He should come more often to APCTP and develop more collaboration. So I think today's lecture is kind of a gentle start up with Professor Misao Sasaki as his new appointment as APCTP Distinguished Professorship. Okay, with this, let's welcome Professor Misao Sasaki, and I will hand over this session to the chair, Dr. Gang. Dr. Gang, please.
Okay, thank you very much, Yunkyu. Before I introduce Professor Misao Sasaki, I would like to ask some of the audiences. I found about 50 audiences participating, and some of them have their mics on. So please make your mic off, except for the speaker and some other person. Okay, let me check. Still, I see some mics are on. It gives some noises in some cases. So, okay, good. One person. Okay, I think this is okay. All right. And other thing is, I was asked that the Misao allows or asks the audiences to use one function when they have questions. So on top of your screen, you can see some function like option. If you put that, then there is some footnote function. So use that footnote function to when you need to write something for your question. So that's what I was asked. Okay, that's done. Okay, now.
Good morning. Good morning.
Yeah.
Well, actually, the audience can also use this function called annotate, and so it is specifically point out which part of the sentence or which figure, whatever he or she wants to know. They have some questions on. So you can just write in onto the screen. And
Okay.
I can erase it, so don't worry. You know, so you can, well, except maybe some immoral type thing we don't accept, but anything you want to accept, you want to write on, and you can do it on the screen. Okay.
Yeah.
This is a function called annotate. I think you can do it.
Yeah. Let me show this function. So, Misao, can you see my mouse?
No, so I don't think it's in the. I cannot see your mouse, but if you write something with your pen or something, there's
Okay.
the pen or lines or, you know,
Oh.
you click the option of the share screen option, and then you have the. Yeah, that's right. Yes, I see it. Yes, nice figure.
Okay.
So what did you write?
Well, something. Okay, you guys can do this.
Yeah.
When you have questions. Okay.
Right. Yes, and then of course, yeah, that's right. Yes, good. All right. So.
All right. We have actually today we have 2 lectures, each 1 hour and 15 minutes. So now I would like to introduce Professor Misao Sasaki. Actually, he doesn't need to be introduced because he is very famous in this field of cosmology. So if you work in cosmology but do not know Misao Sasaki, then probably you should be a spy. But because of this, I never heard any formal introduction before. So this time I would like to introduce him formally. Misao Sasaki studied at Kyoto University and got his PhD in 1981. After that, he worked in various places, including Kyoto University, Hiroshima University, Osaka University, and others. But out of them, from 2008 to 2011, he served as KIAS scholar in Korea. And during 2013 and 2017, he served as the director of Yuba Institute for Theoretical Physics. And from 2018, he's a deputy director of the Kabul Institute for the Physics and Mathematics of the Universe. And he also have other academic activities, like the editorial boards for many journals, such as JCAB, CQG, PRD, EPL, and now he's managing editor from 2010 for the International Journal of Modern Physics, D, and also the editorial board from 2016, Philosophical Transactions of the Royal Society A. And he's also the chair of the Division of Astrophysics, Cosmology, and Gravitation, DACG, from 2015. So as we know, he is a very important personal in the field of cosmology, and there are many good points of him, but I would like emphasize that he is very eager to encourage young researchers So every meetings I attended with him, I found his hotel room that does not know sleep. So he, many young people gather to his hotel room and then just keep talking with drink, I guess. Anyway, this is a brief introduction for him, and he will give a lecture on delta n formalism in cosmological perturbation theory. So, and I was informed that you can ask anytime during his lecture if you have questions. Is that right, Misao?
Yes, 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 it is. Yeah.
Okay, Misao, please. Let's welcome Misao. Yeah.
Thank you very much. Okay, well, let me start this lecture. And as Gunlong said, that questions are welcome. I don't maybe notice, but anyway, you just unmute and scream or say something, or maybe write on the screen with some message to me. Anyway, okay, so this will be a 4 hours plus alpha lectures, and I'm not exactly sure if I can talk all of the stuff I prepared, but in that case, I will just, leave all these slides in somewhere, or maybe just give it to APCTP. So you can just give me questions afterwards anytime. Anyway, let me start. Wait a minute. So, oops. Okay, so these are the kind of references. I mean, these lectures based on it's highly, as you can see, it's highly biased. It's not just because there are so many others, but I'm a bit too lazy to study other things. So that's why everything is based on what I have done with my colleagues. So if you're interested in sorry, I cannot hear you. Sorry. Can you? Maybe the microphone is not so good. I don't quite hear you. Sorry. Is it okay? Yeah. Well, anyway, so I mean, just for the sake of completeness, I'm just giving a list, and so if many of the things I'm presenting during these lectures are given in those papers if you are really interested in digging into this issue. Oops, sorry. Okay, and finally, I mean, another reference. This is a textbook. It took us about 4 years to finish. They finally finished about a year ago. Is published from this World Scientific. So if you're interested, please take a look and maybe buy some, then I will earn some money. All right, okay. All right, so again, let me just start. Okay, so the contents will like this. The first I will introduce briefly, very briefly, about the inflation and how the inflation produces so-called curvature perturbation and so on and so forth. This is a very, very brief review. I have some question, is it? Oh, yeah, okay. So this is just a comment from Gunnon. Yeah, anyway, and hopefully this will be, well, it won't be detailed, but say has enough information for you to follow the lectures that follows this introduction. And second, I introduced so-called long wavelengths perturbation, which is a linear perturbation, so it's not too difficult. But anyway, this is the starting point of delta n formalism. So as I will introduce this and then go into this delta n formula. And then you go to the most important part of this delta n, which is the nonlinear extension. and nonlinear formulas, and also the conservation of nonlinear curvature perturbation, etc., etc., etc. And finally, I touch on this issue of, because these days people talk about various kind of different sort of frames, like Einstein frame, Jordan frame. Maybe these days they talk about disformal transformation and all these things. Anyway, so this transformation changes geometry, and on which you discuss physics. The question is whether this change of the frames, conformal, especially conformal frames, can change the result. The answer, well, I will show later that maybe tomorrow afternoon, is that they actually, given some reasonable assumptions, the result is independent of conformal frames. Okay, all right. No, oops. Again, cool. Yeah. So now let me just introduce talk about something about the inflation and curvature perturbation. And inflation is the almost quasi-exponentially expanding stage in the very early universe. And well, as probably most of you know, that it has become the standard model of the universe now. And most important, the original inflation was proposed to solve so-called some singularity problems, or maybe a flatness or right homogeneity problems of the standard model. But these are, of course, I mean, it's in some sense it is partially solved by inflation, but it's not really the important part of inflation. Most important predictions or the outcome of the inflation is that it can provide a seeds for all the structures in the universe, including us, including Earth, the human beings, living creatures, everything. Of course, the galaxies and class of galaxies, stars, and everything. But anyway, so that's the most important part, and the origin of such structures is considered now to be from the so-called quantum vacuum fluctuations, which I will touch soon later. Okay, now, so, is there any questions? Is it okay? Now, what this means actually is that this is actually the heart of delta N formalism, and I'll come back to this equation again and again, but essentially it's the Friedman equation, or 0, time component of the Einstein equation, which tells you in the left-hand side is essentially the curvature of the space-time, sorry. The h is the Hubble expansion rate. So 3h squared term, in some sense, represent the curvature in the directions of time. 3k over a squared, that's the spatial curvature. When k is positive, it's the closed universe. K is negative, it's the open universe, and so on and so forth. But anyway, it's the total curvature on the left side, and which is given by the energy density on the right-hand side. So once you have some matter or energy in the universe, that will drives the expansion or contraction, but usually the expansion of the universe. It can, of course, change the order of the time, and it can describe the contracting universe. But here we focus on expanding universe because our universe is expanding. Okay, and especially when the rho is almost constant, you have inflation, and then because of the inflation, essentially the original this curvature term this behaves like 1 over a square, is the scale factor of the universe, just simply goes away, and you end up with the exponential expanding universe. And but that sort of a curvature term, which sort of went away, is actually the most important part. I mean, it's not the part which went away, but then as I will describe, this quantum vacuum fluctuation actually generate a new fluctuations in this curvature, and this gives rise to all the structures in the universe. So this will be a, but as you could see, this will be anyway. It's very, very tiny in the beginning, and then gradually, as the universe expands, and after inflation ends, this becomes important. May. So this is a kind of a space-time diagram or scales of the inflation universe I always show. Well, different from the standards of space-time diagrams is that in this figure, it's the time is in the horizontal axis, and space or spatial sort of scale is on the vertical axis, because scale is what we are interested in. And everything is written in so logarithmic scale, meaning so this is the log of scale factor, which essentially it's number V4. In the expansion universe, if you consider the size of some characteristic size of the universe, whatever the size it is, I mean, it's so-called co-moving size. Let's assume that we can have this so-called observable size of the observable universe today, which is defined by so-called Hubble scale, which is in units of length, it's like 10 to 28 centimeters or something. But anyway, so this scale of a universe expands like scale factor. So in the logarithmic scale, everything in essentially it's a linear, say a straight line with some, I mean, depending on the scales of logarithmic scale and of the lengths and the number of equals, they can be just made to 45 degrees or something. But anyway, while the actual so-called the Hubble horizon scale, which defines effective causal scales at each time of the history of the universe, is behaves like this blue curve. During the inflation, essentially the expansion rate is almost constant, which means that the Hubble scale is almost constant, and usually it's constant to last about 60 folds, 50 to 60 folds. I mean, at least because the observable size of a universe today corresponds to about 60 folds during the inflation, right? And then after inflation, well, there may be several different stages of the universe, but in the most standard sort of scenario, most of the number of folds are spent by so-called radiation-dominated universe. So, so in this case, and up to quite recently today. Now, of course, today the dark energy, which is essentially the same as the cosmological constant, start to dominates again. So you may have some different future like this, but in any case, up to the present. So this is kind of the picture you have. You have so during inflation almost constant in a Hubble scale, and after the universe became radiation dominance, this Hubble inverse actually is proportional to a square. Okay, so this is proportional to a square, and this is proportional to a, and which means actually the this length in the logarithmic of a unit, the number of for unit, is about the same. Okay, so this means that the depending on, of course, your scenario of the inflation, so the scale may be larger or smaller, but typically, if the scale which correspond to the current horizon scale left, so we say left go out of this Hubble horizon scale during inflation is like 60 e-folds, number of e-folds before the end of inflation, then we would have about same number of e-folds from the end of inflation up to today. So total number of e-folds would be about 120, which is just the ratio of the scale in logarithmic scale. So this is the characteristic sort of number or scales you encounter in the inflationary universe. Now the important point is, of course, because the fluctuations, I'm sorry, the all this moving scale goes out of the horizon and come in. Any moving scale will just give you a straight line, so it goes out of the horizon, come in. So, so if you go trace back the line, then it will end up with a very deep inside the horizon, and what we assume is that because of this sufficiently large number of epochs during inflation, essentially the universe in small microscopic scale is vacuum. And if it is essentially vacuum, only thing you have is the vacuum fluctuations. But because of this exponential expansion, those vacuum fluctuations will be stretched, and the scale of those fluctuations go out of the horizon. When it comes out of the horizon, it cannot oscillate. By definition, the oscillation means the propagation of the causal structure, but this is a causal region. Locally, as I said, effectively, this is beyond the scale, nothing can communicate, which means that those fluctuations freezes out. And those frozen fluctuations turn out become a curvature perturbation and end up in a so-called density perturbation and form all the structure today. So that's how the inflation works. So most important thing is that the things goes out of this effective horizon, causal horizon size and come in again. Okay. Now, as I said, it's so in this deep inside the horizon, you have some vacuum fluctuation, and that's assumed for here in the case, it's simplest case when you have some scalar field during inflation, which causes those fluctuations. And if those scalar field has the mass scale, which is much smaller than the Hubble scale, or essentially if it is a massless field, then fluctuation of those massless field follows this equation motion, delta phi double dot plus 3h delta phi dot plus omega squared delta phi. And 3h is due to the expansion universe, you have the friction term. Omega square is given by k squared by a square. And as the universe expands exponentially, this a square term quickly goes to 0, and which means that this term, omega squared term, quickly goes to 0. And so this is a harmonic oscillator with friction term, and if the Hubble constant is almost a constant in time, then this is just with a constant friction term and time-dependent frequency omega. So when omega is very large, or in the very early stage of the universe, this term will dominate over this Hubble friction. So you will have oscillations, but because of friction, this will be a damped oscillation. But as time goes on, this quickly goes to very small, and if it becomes very small, then friction becomes most important. So it becomes a friction dominant stage, and end up essentially when it goes to 0, delta phi ceases to move. So it stops at some point. And this fluctuation, which you don't know where you stop depending on the phase of this delta phi, is the source of all these all the structure of the universe. So therefore, you have some initial vacuum fluctuation, which is is stretched out to the horizon scale, and so how to say, mathematically, the reason why this is frozen to some constant value is due to this friction term. Physically, as I said, when it goes out of the horizon, you lose all the contact and you lose all those causal effect, which means that the fluctuation can never oscillate. Oscillation means, because non-trivial k means that it's propagating, but it cannot propagate information outside the horizon. So that's why physically this freezes out, and this is the cause of all these fluctuations in the entire universe. And by the way, during this lecture,
So,
yeah,
I have question.
Oh, yes, please.
As a big, as a, oh my God. Sorry.
Now it's okay.
Can you hear me? Yeah.
Yeah.
As
As
a
an outsider of this field,
uh,
Yunkyu,
Yes.
the echoing is occurring because probably you have two mics in the same place.
Probably.
So you may use this research support office mic.
It's on or off?
If you close your mic, or vice versa.
Now I think it's okay.
It's okay.
Yeah. Now it's okay.
I just wanted
Oops.
off. Yeah. Not together. Okay. Can I? No. Cool.
can you hear me?
Now it's good. Yes,
Okay.
I do hear you. Okay, please.
Sorry to ask this
No,
extremely
it's okay.
question, but said the Hubble constant H act as a friction, but from outsider of this field, I ask what is the fundamental origin of this friction?
Oh yes. So this is well, the very good question. It's because of the expansion of the universe. So when the system expands, as you know, the system works against the expansion, right? So essentially, if you consider, for example, the energy density of those scalar field, energy density must go down, right? Because of the expansion. Yes. So this gives you the a loss of energy, and actually the friction term is it's the same. I mean, so you have some damped oscillations, let's say, and when you have damped oscillations, then energy of the system is gradually lost, and this loss actually is sort of effective, and in the case of cosmology, it's because of expansion. Expansion of the universe, you lose energy. Yes, the system works against expansion. Okay.
Or because universe is expanding and the
Yes.
whole universe.
Yeah. Well, it's yeah. Well, let me just sorry. Annotate. Okay. So as you know, well, in the let's assume the some thermal equilibrium, whatever. I mean, it's the same sign. Huh? You have the dE plus PdV, right? Equals 0, right?
Here,
And if this is positive, if it's expanding, then you lose energy. Huh?
I see.
Yeah. So that's the cause of the friction.
For thermodynamics.
Well, essentially it's the same. I mean, this is for thermodynamics, but even for any system, if a system expands, the pressure works against the expansion, and which means that system's energy is going down, right?
Yeah, but if I imagine the whole universe is as a box, then when you say pressure, then finite pressure should exist outside the box. then can I imagine?
No. So in that sense, yes, I mean, at the leading order, you can assume the universe is essentially homogeneous everywhere. And if you just take one so-called co-moving size of the universe, then nothing moves away from this co-moving volume, because everything is in equilibrium, a pressure equilibrium. Yes. Okay. You have the pressure to go out, but you have another pressure to go out from the other side. So it is in that sense, any co-moving volume is in the equilibrium in the sense of force, not in thermodynamics, but in the sense of force.
I see.
Right? Yeah. But the space itself is expands. So you see.
Here another question related to Hubble constant. Edward asked, where is the origin of this number 3 in front of H?
Oh yeah, that's dimension, 3-dimensional.
Oh, 3-dimensional. Okay.
Yeah. Space dimension. This comes from the dimension of the space.
Okay. Thank you very much.
You're very welcome. Yes. Great. Okay. So this is what happens, and then now this is the source of fluctuation. So you have the quantum vacuum fluctuation, which is frozen outside the horizon. Now, how this becomes the curvature of this space-time? This is the most interesting or maybe tricky part of the inflation, and actually this is very much related to this delta and formalism. Is that so during inflation, essentially you can assume the fluctuation. This universe is dominate essentially homogeneous and isotropic everywhere. But you have some small quantum vacuum fluctuations of delta phi, yes, on this slice. But when the inflation ends, actually this physics, local physics, is determined by, say, in the case in this current in this simple case, is the value of scalar field. If you have the same value of scalar field, like a phase transition, it should be determined by the value of scalar field itself. It's not by spatial curvature, because the curvature in the leading order is completely negligible. It's in some sense because of the equivalence principle, the locally universe is always flat. So at leading order you can ignore the geometry locally, and all the local physics is determined by the let's say some scalar field, in this case, the field which drives the inflation, so-called inflaton field. So the end of inflation is dictated by this red T constant hypersurface, where the delta phi is 0. Yes, it's a homogeneous. So the transition occurs on this surface. Now, but this is different from this hypersurface, where essentially curvature is 0, but you have non-trivial fluctuations. So this is kind of a gauge transformation on the coordinate transformation, but it's a physical, meaningful transformation. So once you consider the universe after this, what we call reheating or end of inflation, hot Big Bang universe, then all the physics is the same on, let's say, delta phi equals 0, or maybe if it is converted to radiation, it's the temperature is constant slice, or maybe you can just call it the density, uniform density slice. But because of the difference between these two slices, they will have non-trivial curvature now. You see, so the initial vacuum fluctuation now, after inflation, when it is summarized to a hot Big Bang universe, changes into a curvature perturbation of the universe. So that's the that's the mechanism. And so once you know this, then it's very easy to understand how to compute these things. But anyway, so this is maybe the most important point of the inflation and delta n. So if anybody has some questions, is that okay? Yeah, you can ask me later if you want. Anyway, So now, and then given this, and then you can, given some model of inflation, you can of course predict the what kind of fluctuation you have. And after you have these curvature perturbations, then this curvature perturbation drives how to say, gives rise to so-called density perturbations, and then but at the same time it gives rise to the so-called CMB, cosmic microwave background anisotropy. And I'm sorry, I don't have any time to introduce CMB, but anyway, so that's the thing. So it's the temperature. Huh? This hot universe temperature will temperature of the universe will go down, and at certain epoch, again given by some time t, universe becomes transparent to those photons, and the photons start to free stream. Now, so that's we call the last scattering surface of the photons, but you do have some non-trivial curvature on those last scattering. And because of this non-trivial curvature, you have essentially non-trivial gravitational potential, and that induces a so-called gravitational redshift. And that's, of course, and many other important effects, but that's the most important components, and which introduces a fluctuation is the CMB temperature. And this is the very recent result by Planck. This number is the number of the paper. They have, I don't know, 30 papers or something, and this is the 6th Planck 2018 result paper. Anyway, so you have this very nice fluctuation spectrum. The horizontal axis is the angular momentum, or the multiple components, the decomposition in the sky, and this fluctuation sort of spectrum agrees very well with this blue line, which is just one of typical model of inflation. So cosmic microwave background result is completely consistent with the prediction of inflation, and which at the same time means that the linear perturbation theory seems to be valid. So for the moment, oh, by the way, so amplitude of this is not so easy to see, but it's microkelvin square, and so essentially it's about in terms of delta t over t, about if it's 10,000 or maybe 100,000, one out of 100,000, 10,000. Something like this. It's a very, very small fluctuation. Anyway, and here I don't show it, but by analyzing the statistical nature of those fluctuations, then they find it's very, very Gaussian too. So this nature of Gaussian nature, as well as this very good agreement with the prediction of inflation, tells you that most probably, I mean, we don't have any other sensible theory at the moment. Those quantum vacuum fluctuations, which is in some sense by definition Gaussian, is the source of all these fluctuations, and which gives rise to all the structures in the universe.
So,
yes?
I have another question.
Mm-hmm.
Excuse me, because I am
yes, please.
ignorant of this field. So when I look at this data, it said,
Mm-hmm.
you said it tells you which describe almost Gaussian curvature fluctuation or perturbation.
Mm-hmm.
So which feature of this data just tells you this is Gaussian curvature perturbation?
No, sorry. Yeah. This doesn't. I mean, I don't have a picture or the diagram for that. But as far as the Gaussian property is concerned, you have to do a different analysis. You have to do whether you assume some non-Gaussianity, and if such non-Gaussianity is present there, or so on, and then you have to say kill those models. Yes.
So fine. Then the question is, again, I'm very sorry to ask this, but by the way,
no, it's okay.
all theory based on this fluctuation of phi. You said this inflation field. What is it? Is it physical or is just some?
Well, that maybe there may be some debates. Yes. Well, not we. Maybe I should say. I think it's something very fundamental physical, which we have not found yet. It's some kind of like a Higgs field. Yes.
Observable in principle.
Yeah. Yes. Right. That's it. That's the my hope. Of course, it may not be, but yes, that's the what we think.
So anyway, this phi field is something physical.
Yes.
And should be observable, but not yet observable.
Yeah. Yes. I mean, for example, some people think actually this Higgs field itself, maybe this field. And but then you have to look for some evidence, huh? Right. And so far we don't have any evidence, and what kind of field it is, whether it is Higgs or something else. We don't have any idea yet. Yes, good. This is really a future issue or problem. Yes. Okay. Yes.
Thank you.
Misao, I have a question.
Hi.
Like Vafa's recent work and his, basically, well, the distance conjecture fit into this, right? This trans-Planckian censorship conjecture, right? I mean, because this essentially places a limit on how far the field can displace, right?
Right. Yes. Yeah. But so as a cosmologist, I would just ask the string theorists to solve their own problem. Okay.
But furthermore, saying this is a problem for cosmology, right?
No. It's a problem in string theory. No, it's the other way around. We have the observations, so we have the results. Yes, and the string theorists should be able to explain that result. If they say that it cannot be explained, it's their problem.
Okay, but I think what they're saying is basically somewhere in your analysis, basically you have trans-Planckian displacements.
No. Of course, I mean you may have. I mean it doesn't matter. I mean you may have some sort of models where there's no trans-Planckian motion or anything. Yes, there's it all depends on your model. But the whole point is that we do hope that there is actually this trans-Planckian sort of how to say journey. Yeah, I mean in the sense of scalar field. And in that case, we will definitely see the gravitational waves within a few years. Yeah, and then once we start to see them, then it's not the problem of cosmology, but problem of string theory. You understand the point?
Yeah, perhaps. Okay.
Yeah. All right. Anyway, so for as for now, I don't. I focus on, say, in some sense, gravitational sector, and maybe there are some, all these conjectures based on string theory and so on and so forth, but for the moment, just leave it aside, okay? Focus on a pure classical gravity plus some quantum fluctuations. Okay, this is just a small comments that so if you do some a reconstruction of this spectrum behind this CMB fluctuations, then in the most simplest case of assuming this power law type a spectrum, you find it's very nice, fit to a very nice power law with slightly tilted, in this way, the horizontal axis is K, and the larger K on the right-hand side. So this means that it's become bigger on small K, and this is we call red tilt. So you have this red tilt, small but finite red tilt. If you this is number of points, I guess, when you reconstruct this spectrum. You increase the points, then you lose information from the both sides, because on the left-hand side, this is too large scale. You have too small observational point. On the right-hand side, the resolution of all these observation becomes bad. So as you can see that if you start increasing the number of points, then actually only thing we can see is that there definitely must be some regions, about a couple of orders magnitudes, where this power law behavior is correct. But beyond that, nobody knows. And that's another interesting point, which can accommodate many interesting physical theories and gravities and so on and so forth. But at the leading order, if you do assume this, then that simply, it fits very well with this slightly tilted parallel behavior. And this is consistent with most sort of simplest models of inflation. Okay. Oh, yes, by the way, so this is this so-called constraints on model of inflation. Of course, there are millions or maybe more of inflation models. So when you draw this kind of diagram, I mean, you have to fix what type of model of inflation you are interested in. Here, and what the Planck people did is that they just focus on so-called single field slow roll model. So you have single field called inflaton, and this inflaton is the cause of everything. That's the most simplest model of inflation. And even in that case, you have various different types: parallel, R square, V, phi square, phi 4 over thirds, and so on and so forth. There are many different models, but anyway, the whole point is that given the model, you can compute the so-called this primordial tilt, and also tensor to scalar ratio. This is the scalar perturbation I just talked about. Tensor I have no time to say, but as I said, it just briefly mentioned before that you do have some so-called gravitational wave fluctuations, or gravitational fluctuations of the background, and those background gravitational fluctuation produces the gravitational waves background in the universe, and this you have this ratio is called R, which depends on K. But if both are almost scale invariant, essentially this would be about constant in K. But in any case, given some certain pivot scale of K, this ratio is the observable, and which you can test, by which you can test the inflation models. And the current sort of observable bound is that this tensor to scale ratio is somewhat below 0.05, sorry, 0.1, definitely less than 0.1, maybe probably less than 0.05. And it could be about 0.01 or something. While the tilt is very well determined, which is like 0.965 or something. So that's the observational results, and all these different sort of curves or lines tells you the prediction of all the models. And currently, the best fitted model is so-called R square inflation model, or this point or here, the Stravinsky model of inflation. But of course, this doesn't mean that this is the model of inflation. It's just, it is consistent with observations. Any questions? Okay.
I have a question in the previous slide.
Yes.
I'm just curious about this. In the lower right figure, the uncertainty band becomes suddenly wide. This width of
the rightmost one. I'm not exactly sure. This is marginalized. And so, if you allow me to just delete this figure, remove this figure from
anyway, then except for n equals 2 case, the uncertainty becomes so quickly grows in right band only. So is this matter of physics or the resolution?
No. So as I said, on the left-hand side comes from this so-called cosmic variance. You cannot beat this. This is always too difficult. The right-hand side, yes, is from the because of the loss of resolution. Yes, angular resolution.
Thank you.
Right. Yeah. Okay. All right. But in any case, so as I have shown, I mean, this is the simplest case. So you may, if the simplest model of inflation is really the case, then you know that must be fitted in these observations. But of course, as I said, I mean, as soon as you include some other different points, then you know, the spectrum doesn't have to be just simple parallel, and maybe there are some different sort of you know, other fields coming into play and so on and so forth. So you may have some many more complications. So as I said, for example, tensor scale ratio is another sort of a nice observable, which we hope to be observed. They be able to be observed within 10 years or so. If, for example, this a project called Lightbird goes success. Anyway, and of course, as I said, at leading order, the fluctuation is essentially Gaussian. But let's say this is Newtonian potential, then you have so as well, this Newtonian potential results from so-called this curvature perturbation, and the curvature perturbation introduces Newtonian potential, and Newtonian potential introduces the gravitational attractions and the density perturbation and so on and so forth. Anyway, so these fluctuations, as I said, at leading order is Gaussian, consistent Gaussian, and this amplitude is about 10 to minus 5. So even this, if you how to say, parameterize this non-Gaussianity by say going to phi square, coefficient of phi square, which is we call FNL. Since this is 10 to minus 10, unless Fn is very large, it's still very, very close to Gaussian. But in any case, this Planck data is so accurate. Actually, they can constrain this FNL to about order 1. I mean, so it's well, a little bit bigger than that order 1. But anyway, but still, this means that so FNL over order 1 is still possible, and this order 1 FNL actually can constrain many different theories very considerably. So this is another still a very, very important sort of a direction of research. So in any case, well, this is a sort of some other models about other than the single field model. Of course, you have multi-field, may have some non-Slorol regions, may have some theories based on string theory, which may be much more complicated. Maybe you have some vacuum bubbles occurring or collisions of those bubbles during inflation and so on and so forth. Anyway, so you may have many different models, type of model of inflation, which should be tested. I mean, if they are viable enough. And so for this, at the moment, it seems that the simplest and most useful way to compute such a fluctuation is to use the data in formalism, and that's the whole point of my lecture. And so now I have to tell you what data n is, and I don't maybe this explanation is not so good, so maybe I should do it later again. But anyway. Definition is that it's simply the delta n is the perturbation in the number of efforts counted backward in time from a fixed time, and so this is very similar to using the so-called redshift. When you in cosmology we identify the say some early universe time by redshift. For example, if I call the redshift of 10, means that some say photons propagating from that to the current time will be redshifted by a factor of 11. Yes, 1 plus z is the redshift factor. So, but the larger redshift means that the sort of more past in time, and the number of efforts counted backwards is essentially the same. I mean, it's in some sense the logarithmic of some redshift. Okay, So the fluctuations number equal means that the fluctuations in, say, redshift at certain given epoch in the past, not today. So, so this since the number of equal by definition is defined by two different points, some initial point and final point, and if you so this non-local in that sense, it's the non-local entity, and the fluctuation delta n is essentially delta n caused by some fluctuation, let's say, of some event in redshift. So so this is the definition of the delta n. Now, this final time, you can of course choose at the current time, but that's not so convenient because we'd like to sort of evolve those fluctuations to see what kind of CMB fluctuations or maybe the large-scale structure you can have from some initial condition of the universe. So we'd like to choose this final time to be sometime during radiation dominance. Now, this radiation dominant stage, we usually think by that time all the universe becomes so-called adiabatic, in the sense that, for example, this is just an example, but in our universe you have the baryon numbers. Say per photon is like 10 to minus 10, number, very small but finite number of the baryon numbers. But if you have this fluctuations in the baryon number independent of the number of photons, then this is so-called a entropy perturbation or isocurvature perturbation. And then you have a different sort of source of fluctuations. But if there are no such fluctuations, then essentially given, as I said, given maybe, I didn't say so yet, given some temperature or some physics of that time in the early universe, you can just solve the following, say, how the universe evolves after that uniquely. So this uniqueness in the evolution of the universe is is called adiabatic in the cosmology, in the terminology of cosmology. So cosmological perturbation, sorry. So when the universe becomes adiabatic, means that once there's no ambiguity in the evolution of the universe after a certain time. For example, we know the baryon numbers of the universe and which is homogeneous all everywhere and so on and so forth. Then you choose that time, and then we know that fluctuations, the fluctuations on very large scale will not evolve if under this adiabatic condition. So given, if you compute delta n under this condition, then you know it can be used for the initial condition for the evolution of the data universe. So, okay, so this is what you have to do. Maybe this isn't so clear to you. So gradually, I hope during this seminar, lecture, it becomes clear. Anyway, if you have any questions, just ask. It's okay. Yeah, maybe this is a bit too abstract. Anyway, so now what is known is that this delta n turned out to be equal to this so-called curvature perturbation, conserved curvature perturbation, and which is actually true even up to nonlinear level. And so that's why this is very important. I will show you this later in this lecture. And the important point is that this curvature perturbation actually comes into this computation of the spatial curvature. So at nonlinear level, it's quite complicated. Complicated expression, but the whole important point is that even this nonlinear level at the some sort of leading order approximation, where to consider some large scales essentially, this, because the curvature perturbation is conserved, all these quantities will be just only space dependent. Only time dependence is through this scale factor a squared. So essentially, this can be written in this form 6k divided by a square, and k just depends weakly on, say, some space. Any questions? Okay. So now this comes back to this the Friedman equation I showed in the beginning. So in the case of general relativity, this curvature comes into this expansion. Hello? Any questions? Oh, who is this? If you have any question, if you are not question, then may I mute you? Okay. Okay. So now you have a weakly spatial dependent curvature term, and then in the early universe, because of this 1/a square, well, the energy density usually behaves like 1/a to the fourth in the early universe, in the radiation dominant universe. This is completely ignorable, but as the universe expands, this gradually becomes very important, and this curvature term essentially drives the matter to fall into, say, gravitational potential and form large-scale structure and so on and so forth. And the important point is this is the case of the general relativity, but this formula, spatial curvature formula for scale curvature, is valid essentially for any theory, not any, but the most theory of gravity. It's like I would say what you call covariant theory of gravity. Yes, without which has a standard sort of gravitational degrees of freedom and so on and so forth. So another important thing is that delta n formalism, if you just carefully apply, then can be applied not only to general relativity, cosmology and general relativity, but many other theories as well. Okay, so now about this, how this kind of fluctuations in this number V-fold arises. There are essentially three types, which arises in the later discussion. So one is that the so-called originally already adiabatic. These fluctuations, okay, is just some fluctuations in the essentially the initial time. So if you consider some number V4 up to in this case essentially this direction is time, while and as well as some maybe some, let's say, some scalar field or something, and you have, say, two fields case, and assume that the main sort of evolution of the universe is along this straight line. Yes, then if you can completely ignore the degrees of freedom of phi1, then fluctuations of phi2 would just generate the fluctuation in the the sort of time. This will cause a number of V-folds, and so that's the standard case, standard single field slow inflation case, which is the simplest case and the most easy to understand. Other cases a bit complicated. You essentially have other degrees of freedom. So you may have two different trajectories of the universe, and originally maybe difference may be small, but maybe you have two completely different paths, depending on the say model of your let's say scalar field cosmology, and when these trajectories meet to become, say, adiabatic. Adiabatic limit means that the trajectory becomes unique. So the unique trajectory, you assume that the universe end up with some unique trajectory, which is the adiabatic limit. So by that time it approaches this, then number of V-fold, say, from this right trajectory may be substantially different from number of V-fold from left trajectory. So in the end, you will have some huge difference in number of V-folds. So this is the case when you have the entropy or isocurvature perturbations, which doesn't sort of play important role is during this cause of course of evolution can end up with very, very important fluctuations in the curvature. This is the rightmost case is fairly simple, the same as the second case, but the point is that this can happen at once by some kind of phase transition. So again, in this case, the phi-1 direction doesn't produce anything during the most of time of the evolution, but at certain point you have some phase transition, and then which drives the universe into the adiabatic stage. But this transition time may depends on the value of phi-1. And in this case, sorry, somebody has some questions? Is it okay? Okay. Yeah, just say something if you have questions. if you just stay silent, I cannot see anything. Anyway, so in this case, as you could easily see, even if you start with completely exactly the same value of phi-2, yes, phi-2, difference phi-1 would end up with difference number of E4 in the end. So this causes another, this can be another sort of source of delta n, or the curvature perturbations. Okay, so this figure is most important. So as I said, this figure as well as this one, the fact that some fluctuations in some scalar field will change into the curvature perturbation, and this and because of this, this fluctuation will be the source of all this curvature perturbation, and this fluctuations delta phi actually results in the fluctuations number of E4s, and which gives rise to the curvature perturbations. Okay. Okay. I think
can
maybe.
I ask a question?
Sure, please.
Can you turn back to the just this slide is okay. So why should we choose the final time slides to be the co-moving slides, not the spatially flat slides?
Yeah. So this is related to this let's say focus on the GR case. Now,
yeah.
If taking flat slides means that you don't have any curvature perturbation, right? But instead you have some fluctuation density. So, but it may be okay. I mean, it's in some sense matter of how you express things. But instead of considering such slides, if you consider, for example, this a uniform density slides or something, then you can include this curvature term, and this curvature term, as I said, the good point is that this curvature perturbation on so-called this uniform density slice or the co-moving slice is conserved.
Yeah.
Yes. Yeah. So on that slice, you can write down. You can sort of extend this Friedmann equation to local Friedmann equation, where K depends on space.
Yeah.
Hey, H square and rho, they do not depend on scale at leading order because they dominate in the very early universe. This is just minor small correction. If I write it, maybe it's better. Okay. So rho will be proportional to 1 over a force in the early universe.
Yeah.
Right. Oops. It's not so easy to draw. Sorry. But I guess you.
Yeah, a to the minus 4. Okay.
Yeah, a to the minus 4. A to the minus 4, huh?
Yeah.
Right. So this will dominate, and which means that this and this will be the most important part, and this is almost negligible in the early universe. Yes.
Yeah.
But in this slice, actually, you can just focus on the small correction, but they assume this is x dependent. Yeah. and you can evolve the universe, and as if you are in the locally Friedman universe. Yes, and then you can. It's very easy to predict what would happen in the later universe, right? But yeah, so that's the very advantage that you use the slice where this so-called curvature perturbation is conserved.
Okay, fine. Thank you.
Yeah, well, yeah, maybe you can ask me questions later. You know, we encounter this kind of expression many times. Yes.
Okay. Yes. Thank you. Thank you.
Okay. So,
excuse me, I have another question.
Oh yeah.
Okay. I have why is the iso creature perturbation sometimes called the entropy perturbation?
Yeah. Why?
Why? Yes, why?
It essentially it is fairly similar. I mean, maybe the originally it's as I said in the case of our universe, in the very early universe, our universe is essentially dominated by radiation, but you may have some very small number of baryons or maybe cold dark matter. They behave like matter. So in the early universe, their sort of a contribution to the energy density is negligible. Now, but if their density is fluctuating in spatially, then you can always define this as I wrote before. Yes. Some number of something like baryons, yes, divided by photons, and these fluctuations can be non-vanishing, meaning that and this is essentially you can invert this, and then since our universe is essentially dominated by radiation, so this will be a entropy per baryon, entropy per baryon, and the fluctuation is this will be the fluctuation of the entropy per baryon. Do you understand?
Okay.
If this is non-vanishing, and so this is the source of the why we call entropy. Yes.
I see.
But so from matter point of view, so this is from matter point of view, and this is from a GR or the geometrical point of view. So they sort of essentially very similar. I mean, it depends on which side of the problem you see. It's a different aspect of one same thing. Yeah. Okay.
Misao, so is it impossible that adiabatic perturbation is converted to entropy or iso-curvature perturbation?
No, I don't think so. No. So as you could easily see, I mean, it's oh, of course, no, it's not conversion, but if the dominant. So, for example, if our universe is you think that it end up with certain type of adiabatic limit. So now you have all the other perturbations and so on. But all of a sudden, there was some unknown component of the universe, which all of a sudden becomes dominant, and they dominate the whole universe. Then they don't disappear, but they become negligible. Yes. The original idea of perturbation can become negligible depending on the how the universe evolves later time. But if you assume a universe reached the adiabatic limit and there is no other possibility of entropy or iso-curvature source, then yes, it's unique. I mean, you can never. I mean, that's the curvature perturbations you can never delete, remove.
Yes, thank you.
Yeah. So essentially, again, it's the same. If you just look at this equation, and this is just a Einstein equation, or maybe in general theories, it's the Hamiltonian constraints. and this constraint cannot be changed. I mean, unless you violate some fundamental physical rules. Okay.
Okay, Misao?
Yes.
Time is almost over.
Yeah, right. So maybe I should probably stop here, and then maybe people have some questions, and I can just stay on this Zoom for another 10 minutes or so, 10, 20 minutes, if you want. Yeah.
Okay. We stopped his first lecture here, but he's taking questions.
Now, I have a very simple question. It's about delta.
Yes.
Delta N is basically defined in terms of redshift, right?
Yeah, right.
I mean, so this just seems more a mathematical tool than, I mean, how would you define redshift here, right? I mean, if it physically, it probably doesn't have any meaning. It's more a mathematical thing, right?
Oh, yeah. I mean, are you saying that can it be actually observable?
Yeah, I mean, what would you say? Redshift in neutrinos, or you know, how would you? I mean, it seems just like a mathematical thing.
Yeah, it is. It is. I actually, as a so the whole point is this. So actually, what we do is that we compute the number from this, say, hypersurface, some T called temperature equals constant hypersurface. Then automatically you see that this sort of a flat slicing up to the flat slicing number of it will be different from here and from here, right? So this is this means that you have some slight number of a fluctuation in the redshift or number of efforts. Okay. So it's the I don't know. I mean, am I clear enough? So it's the this number of efforts between these two slices, huh? And from here, for example, and then if you will have a difference, huh? Let's say difference, this difference.
Okay.
That's the number of difference in the number of efforts. Okay.
Okay. Thanks.
Yeah. Okay.
Okay. Any other question?
So I have a question. So I think I missed something in the last diagram you showed.
Which one?
Isocopature and tree diagram.
This one.
Yeah. So you mean the last two diagram generate the isocopature perturbation? Because
yeah. So let's say this this horizontal direction is as curvature. I mean, so changing the value of this, let's say phi1 from this value to this doesn't change the evolution of the universe at all. So that this means that it's isocurvature component. Let's say, for example, this is the blue scalar field. This is a red scalar field, but the color doesn't change any geometry. So you know, you have two different sort of colors, but the colors doesn't show any. It gives rise to any fluctuation in the geometry. So this is the isocurvature perturbation.
And what do you mean by the adiabatic on the bottom? So you have
but once they, so when I say adiabatic limit means that so the trajectory of the universe becomes unique. Yes, some single trajectory in this whole space. Now, for example, in this rightmost case, although let's say I said this is red and this is blue, so they may during this evolution of the universe, at this early time, everything is exactly the same. So there's no difference between blue or red. But when there's some transition, phase transitions, and maybe the phase transition, time of phase transition may depend on the color. For example, the red color, how to say, is slowed has the later transition than say blue color, then number V-fold would be different. Huh? This number difference in the number V-fold between these two will produce the curvature perturbation of this universe, or delta n of the universe. Is this? I don't know. It's not still clear yet.
Yeah.
This is important. So ask me, please.
I have question.
Yeah.
Continuing question about number n. You said it's number E-fold.
Yes.
At the very beginning of your slide, you show some diagram, and it shows inflation period n equals 60, and Big Bang period is n equals 60. So altogether, our universe has this of E-fold is about 120. So this particular number, 60 or 120, how do you calculate, and does it?
How do I calculate? So of course, I mean, as I said, it's almost it depends on what kind of a inflation model you assume. But so the most kind of how say reasonable, or maybe maybe desirable, model of inflation has the energy scale about 10 to 15 giga electron volts. That's about 4 order of magnitude below Planck scale, 3 to 4 order of magnitude below Planck scale. Now, so that's the how to say the temperature. Let's say okay. So from that energy scale, you can compute this the Hubble constant. But at the same time, maybe the simplest is that if you so if you assume this 10 to 15 giga electron volts, then so the temperature of the universe, at the end of inflation, or right after the end of inflation, when start to become radiation dominance, will be 10 to 15 giga electron volts. In terms of electron volts, it's 10 to 20, 24, was it 24? 24 electron volts, yeah? Right. Now, the current CMB temperature is 10 to minus 4 electron volts. So this means that the ratio of the temperature, which is essentially the ratio of the scale factor, is 10 to 28 or something. Yes. And if you take the natural log of this, log of 10 to 28, it's about 60.
I see. So this number 60 for inflationary universe, and another number 60 for the Big Bang universe is just this equal number 60 and 60 is just accidental.
Oh yeah, because essentially most dominant part of the universe after inflation is dominated by the radiation dominant universe, where this length scale, this behaves like scale factor to the square. Yes, a square. This is a, yes, and this is a square. Therefore, the number of E-fold, this length scale of this will be equal to this. If you draw this diagram, triangle. You see.
All right.
Is it okay?
Yeah. Still, I have some question, but
yeah. So it's the accident. Yes, the fact that our universe is essentially radiation dominated. It depends on physics of our universe.
But this power a to a square, the length square,
yeah,
to a square. So this.
This is because of this. Radiation behaves, as I said, rho behaves like 1 over a to the fourth. This is standard matter behaves like 1 over a cube, but because of expansion and a radiation at the pressure works against the expansion, and so decreases the energy density further. So it behaves like 1 over a to the fourth.
Okay.
And the Hubble parameter is, this is proportional to h square. This is h square. Right. So h inverse will be h square.
Okay.
Yes.
Thank you very much.
Yeah. Okay.
All right. I guess there are some more questions, but I think you have to close his first lecture here. So those who have further questions, you can use the time in the afternoon for the second lecture.
Okay.
All right. Before I close this first lecture session, I would like to announce this time schedule. So his second seminar will be 14 to 15:15 this afternoon, and then tomorrow he will give 2 more lectures at 10:30 to 11:45, and then again the 14 to 15:15 in the afternoon tomorrow. So those who didn't know this, then take this time schedule. All right, let's thank Misao Sasaki for his wonderful lectures this morning. Okay, thank you very much.